indicators today. So what is an indicator? We use them all the time, as you've done with your titrations, but really we don't know what they are. We know that they just change color. But in general, indicators are weak acids. Usually organic acids, so they got big complex formulas. But they have different colors depending on if they have a proton attached or not. So, or it's acid and its conjugate base. Okay, that will give you different colors. So we can set up an equilibrium for a general indicator. So H, I, and D. H for the proton, I and D for indicator. So if we have H, I, and D plus water, throw it into water. It's a weak acid, so it'll set up an equilibrium. It'll donate a proton, and you get this equilibrium happening. H, I, and D is the acid, obviously, because it's got the proton. It will have a certain color. We'll call it just color number 1. I and D minus is the base. And it will have a different color. We'll call number 2. So because this is an equilibrium, we can use what we learned in chapter 2, Le Chatelier's principle. We can apply this. So if we put it into an acidic solution, so we have a high amount of H3O+. This is going to increase the H3O+, which is going to push the equilibrium to the left. Produces more of the H, I, and D. And the decrease in the I and D minus. So we get a decrease in I and D minus. And the color would be color number 1, whatever that is. I guess I wrote it in blue, so we'll just write it in blue. So it's the color of H, I, and D, which is color number 1 in this, whatever that is. Now, if we're doing a titration, so that's the beginning of the titration, then we use NaOH in a lot of our titrations. We start to add more base. That is going to react with the H3O+, pull it out of solution, which is going to shift the equilibrium to the right. As it moves to the right, all right, we get a shift in equilibrium to the right. We get more I and D minus forming, and the color will be that of I and D minus, which is, in this case, color number 2. Right? So the equilibrium shifts this way if you add a base. And if you're adding an acid, it's going that way. That's basically what we're doing with the titration. If we were using phenolphthalein, this would be colorless. This would be pink or light pink. At the transition point or the end point, so that is when you have equal amounts of these two things. So we have equal amounts of H, I, and D and I and D minus. Okay, so that gives you the actual color shift, all right? Because if you look at in your data booklet, all the indicators have a pH range. So the midpoint of this pH range is when you get the shift in color. So, for example, if we look at, where's phenolphthalein? Here's phenolphthalein. We use this a lot because we go from colorless to pink. So it's an easy transition to see. And that's going to occur halfway between 8.2 and 10.0. Thymol blue, you're going from yellow to blue. All right. So if I'm correct, the midpoint, or when you reach endpoint, it's going to be green. Okay. That's why we tend to use phenolphthalein, because it's a very distinct color change. Whereas yellow to blue, depending on how you see colors, is it going to be green? Is it when do you make that call of when the color change has happened? So going back to our notes here. So for example, if we had methyl red, it changes from red to yellow. Therefore, the endpoint of your titration is when it turns orange. That's going to be fairly tricky to actually make that call. Okay? So that's the whole theory, and that's one of the questions in your lab that you're writing up today, hopefully, or answering the questions. Why do we choose phenolphthalein? It's a very distinct color change and fairly easy to see. All right, now, because they're weak acids, if we look at our weak acids table, we have diprotic acids. Indicators are the same. You can have diprotic indicators. So that means they have 2 protons. So you can get 2 color changes. So here's the original solution. That's going to be your color number 1. And here we go again. There we go. Color number 1. It's going to donate a proton. It's acting as an acid. I get H IND minus plus H3O plus. This is color number 2. That's our very similar to what we had up there, but we still have another proton here. So it can donate another proton. So you keep adding base. So this is going to be the most acidic solution. We're increasing pH as we go this way. Increasing the pH by adding base. And then we get the second color change where it donates the other proton. Get IND minus, H3O plus again. This was color number 2. So this is color number 2 from here. And then we get our final color change, which is color number 3. Okay. In your data package, an example of this would be thymol blue, which transitions from red to yellow in the 1.2 to 2.8 range. And then again, there's a transition from yellow to blue from 8 to 9.6. So it is yellow all the way through this pH range. And then when we start getting up higher, midway through the pH from 8 to 9.6, we get a change into, change into green and then finally into blue. Okay. So if you're doing a big scale pH titration, it sometimes makes sense to use that. Oh, oops. Okay. So you get 3 different colors basically. All right. So let's look at the equilibrium constants. So we know we have this equilibrium. We can indicate or determine the Ka. So the Ka expression of this equilibrium, because it's a weak acid, is concentration of products over concentration of reactants. So that's going to give us H3O plus times concentration of IND minus divided by, don't worry about the water, concentration of HIND. But halfway through the endpoint, so halfway through the color change, is the endpoint. At that point, you have equal amounts of this and this. Okay? That's the definition of endpoint. So we have IND minus is equal to concentration of HIND. If you sub that into this equation, you're going to get, I'll just sub out the IND minus. These will cancel, and you're left with Ka is equal to the concentration of H3O plus. This is at endpoint. In other words, halfway through the color change. Okay, so what does that mean? Well, if we have the Ka equals the concentration of H3O plus, we can take the negative log of that, of each side. This is pH, and this is pKa. So you end up with the formula pKa of an indicator is equal to the pH. Or, you can rewrite this. Ka is equal to 10 to the negative pH. Okay? This is for indicators. So, and it's at endpoint, all right? So that an indicator changes color when concentration of H2O plus equals the Ka at endpoint, okay, which is halfway through the color change. So what does this allow you to do? Well, we can figure out the Ka of each indicator. So methyl orange, if you go to your data table, booklet, methyl orange, methyl orange, methyl orange. There's methyl orange right there. Has a pH range of 3.2 to 4.4. Okay. So pH range 3.2 to 4.4. Then halfway through that is when we can calculate the Ka. So, okay, well, what's the midpoint of that pH range? That's going to be 3.2 or 4.4 minus 3.2, doesn't matter, divided by 2. So it's going to be added, sorry. 3.2 plus 4.4 is going to give me 7.6 over 2. Basically, this is the midpoint formula. And you get 3.8. That is when we're going to get a change of the color from red to yellow. Okay? So you'll get an orangey color change. All right? That is the endpoint of your titration, essentially. But we want to know, what is the Ka of this acid? Well, okay, that's the midpoint range. It's an what do you call it? Indicator. So we can use this formula right here. The Ka is equal to 10 to the negative pH at the midpoint. 10 to the negative 3.8 gives me a Ka of 1.6 times 10 to the minus 4. That is the Ka of methyl orange. So you find the midpoint of the pH change. The Ka will be 10 to the negative pH of that. And that's it. Gives you the Ka of the midpoint of the indicator. All right. So in the lab last week, we used the universal indicator, and I gave you a bunch of pH color changes. All a universal indicator is when you mix a bunch of indicators together. So for example, if we mix methyl orange, bromothymol blue, and phenolphthalein together, all right, here's the pHs. So at pH 3, methyl orange is red, bromothymol blue is yellow, phenolphthalein colorless. So the combined color at that point at pH 3 will be orange. pH 5, methyl orange now has switched to yellow. Bromothymol blue is still yellow and phenolphthalein is colorless. So at pH 5, we know we'll have a yellow solution. At 8, methyl orange is yellow. Bromothymol blue is blue, and phenolphthalein again is colorless. Yellow and blue will give me a green. And at the end, If we have methyl orange at pH 10, it's yellow. Bromothymol blue is blue. Phenolphthalein changes to our pink color. Mix those together, we will get a purple. Okay, so that means you can test and you get an idea of the color range of your solution, which is what we did with the hydrolysis stuff last week. It just gives you an idea how acidic, is it close to neutral, or is it more basic? So if you put it into the solution and you get an orange color, you know your pH is around 3. It's low. If it's yellow, you know you're around 5. If it's green, you know you're around 8. And if it's purple, you know you're very, very basic at around 10. Okay? That's all a universal indicator is. You just mix a bunch of indicators together to give you a broad spectrum of changes. Okay, so in summary, it's always an organic acid. It's a weak acid, so you get a equilibrium set up. Because it's a weak acid and you have an equilibrium, you can calculate a Ka. We showed above that for indicators, the pKa is equal to the pH, or the one that we usually are going to use, the Ka is 10 to the negative pH. This is at the endpoint or the midpoint of the color change. So you add the range together and divide by 2, and that'll give you the halfway through point of the color change, okay? And then you can calculate your Ka and answer any questions that are necessary. All right, people, thank you. Hope you have a good day, and I will see you tomorrow. Please answer the questions on the next 2 pages and or finish answering the questions on your lab. All right, have a good day. Thanks.